In the last class we started discussing about coupled spin system, and also we introduced what is called Poppel nomenclature. Remember, a spin system is the coupled spin system is the one. There could be group of protons in a given molecule, group of nuclei, nuclei with which are all NMR active spins, and there could be coupling among themselves. It could be homonuclear, it could be heteronuclear, does not matter. So long as there exists a coupling between them and all the spins form part of the coupled spin system, it is called a spin system. For example, I have A, B, C, D, 4 spins, could be homonuclear or heteronuclear, does not matter. A coupled to B, A coupled to C, A coupled to D, B, C, D, all are coupled among themselves. One of the coupling could be incidentally 0 value, coupling could be 0, does not matter, AB or AC coupling could be 0, but then AD coupling is there, AB coupling could be there. So that means it is a part of the coupled spin system. One of the coupling could be 0, but it becomes part of the coupled spin system. And this coupled spin system can be classified into two things, weakly coupled and strongly coupled. I explained to you what is the difference between weakly coupled and strongly coupled. Weakly coupled is the one where the coupling separation, chemical separation should be sufficiently larger than the coupling constant. Let us say I have two spins I and J. If chemical shift I, delta I, and chemical shift of nuclei J, delta I minus delta J is sufficiently larger than Jij, it is called weakly coupled spin system. That means you take the different ratio Jij over delta Ij, it is much smaller than 1, 0.01 or point of the order of 0.01, then it is weakly coupled. Or take the reverse of it, delta over J, then its value should be sufficiently large of the order of 50 or even more, then weakly coupled. On the other hand, if the chemical shift difference between the two protons I and J is very small compared to that of the J coupling itself, then it is called strongly coupled. The condition is the ratio, if you take J over delta, it is almost approximately equal to 1, then strongly coupled. Or to take the reverse of that, delta over J, that is also almost approximately equal to 1 or slightly greater than 1, they are called strongly coupled. So, I gave the example of what is a weakly coupled and strongly coupled molecules, measured chemical shifts, measured J couplings, both in homonuclear case and heteronuclear case. And of course, heteronuclear case they are always weakly coupled, because the chemical shift separation is of the order of resonating frequency, which is of the order of several megahertz. As a consequence, heteronuclear coupled spin systems are always invariably weakly coupled. Homonuclear, strongly coupled you can think of only in the homonuclear cases. And I explained to you the Poppel nomenclature. Poppel nomenclature is the one for each spin of nuclei a Roman alphabet is given, and then if it is weakly coupled, the alphabet order the farthest letter is given for weakly coupled, and the letter which is next to each other or closest to each other are weakly coupled. For example, one spin is coupled weakly coupled to another spin, the letter is given, nomenclature is A and X, A is here, X is far away, that is called weakly coupled. If A is here and next B is the letter is given, that means the chemical shift separation is much smaller, that is called strongly coupled. So, there could be many protons coupled, many can be weakly coupled, they are strongly coupled and weakly coupled, we know. If AB is strongly coupled, ABC is strongly coupled, ABCD is also strongly coupled, AX is weakly coupled, AMX is weakly coupled 3 spin, AMP is weakly coupled 4 spin case. This is what we explained. And now going further, you may ask me a question, what happens if there are chemically equivalent spins? How do we give the nomenclature for that? What is Poppel nomenclature for that? Now we will discuss that today about this thing. For example, the nomenclature for the weakly coupled spins are given like this. If I have weakly coupled spins, there is a nomenclature which is given as A prime, a prime notation is always used for chemically equivalent spins. Again in the weakly coupled case, A prime X is given, A prime XX prime is given, A prime MM M X XX prime like that. What is the nomenclature for this? Remember, A prime are strongly coupled, A prime X and this A prime X are weakly coupled. If I give A prime, between A prime they are strongly coupled, chemically equivalent spins, they are called chemically equivalent. X prime are chemically equivalent and A and X are weakly coupled. Understand the logic. A prime X means A and A prime are chemically equivalent spins. Babies, they are between them they are strongly coupled, but each of them are weakly coupled to X spin. Similarly, A prime, between them they are strongly coupled, X prime, between them they are strongly coupled, they are chemically equivalent, these two are chemically equivalent, these two are chemically equivalent, and between A and X, A prime and X, they are weakly coupled. Similarly, you go further, A prime, MM prime, A prime are chemically equivalent, X prime are chemically equivalent, M is a different spin which is single spin. Now, there can be a coupling between A and M, A prime and M, X and M, X prime, and coupling between A and X will be there, A prime and X will be there. They are all strongly coupled, and between A and M they are weakly coupled, between X and M they are weakly coupled, and they are all equivalent spins A and A prime. So, equivalent spins are given the notation prime notation is given. Same thing, if they are strongly coupled, it is A prime B. A prime B means A and A prime are chemically equivalent, they are themselves strongly coupled, plus it is coupled to another proton which is next, which is B, to which it is strongly coupled. A prime B prime means A prime are chemically equivalent, B prime are chemically equivalent, between them there is a strong coupling, they are strongly coupled. A prime is strongly coupled because they are chemically equivalent, there may be a coupling. B prime are chemically equivalent, there may be a coupling, they are strongly coupled, and A and B are strongly coupled, A prime B are strongly coupled, like that. Similarly, you can have A prime, B prime, C, there is no C prime, C. That means A prime are chemically equivalent, B prime are chemically equivalent, together they are coupled to C, all are strongly coupled. This is the nomenclature used for chemically equivalent spins when they are strongly coupled. Look at a molecule like this. This is a orthodichlorobenzene. Now, I can put a nomenclature like this. Of course, we have to mention the chemical resonating frequency, because at some frequency at 100 megahertz it can be A prime, B prime. If you go to 1000 megahertz or 1.5 gigahertz, it can become A2X2. The nomenclature changes. Okay. So, what I am trying to say is this in a particular spectrometer, low frequency spectrometer, these two are chemically equivalent, it is called A prime, these two are chemically equivalent, B prime, it is A prime B prime spin system. Look at this one, this is a different substitution, again these 3 protons, this is A prime, this is B prime, it is a strongly coupled case. What about this one? There is a symmetry axis, these 2 protons are equivalent, these 2 protons are equivalent, I call it A prime, if there is, and this these 2 fluorines are chemically equivalent, this coupling and this coupling are different. So, I call it A prime XX prime spin system. Remember, this is A prime XX prime spin system. This is A prime BB prime, these two are A prime BB prime system, this is A prime XX prime. Why XX prime? Why? Because weakly coupled means I am telling you, look at it, these are all heteronuclei. Obviously, chemical shift separation megahertz and the coupling is so small. So, this is heteronuclear weakly coupled A prime XX prime spin system. Okay, this is as far as the equivalent spins are concerned. What is the nomenclature of chemically equivalent spins when I have group of spins like CH2 and CH3 groups? CH2 groups, there are 2 protons which are chemically equivalent, here 3 protons which are equivalent, it could be chemically equivalent, magnetically equivalent, does not matter, there are equivalent groups. Then what nomenclature we have to give in such spin systems? What is the nomenclature we have to use when there are equivalent protons? Remember, we have to use what is when they are chemically equivalent, we give prime notation. When they are equivalent groups, we use a subscript like this. That means if I say AB2, that means there are two protons which are chemically equivalent. A2B2, there are two protons which are chemically equivalent, two groups. It is a CH2 group like CH3 group. If a CH3 group will be there, may be there. So, for strongly coupled spins, if the chemically equivalent spins are present, we use the nomenclature with a subscript. The subscript number refers to number of equivalent protons. For example, if I say AB2, there is there are two protons which are chemically equivalent. There is a group of protons which are chemically equivalent is 2 here, CH2 group may be there. There are 3 protons which are chemically equivalent. So, subscript refers to number of chemically equivalent protons, and A and B letter tells you they are strongly coupled. So, it means A2B2, there are 2 protons which are chemically equivalent here, 2 protons which are chemically equivalent, between them there is a strongly coupled, that is the nomenclature. You should understand the nomenclature what we are going to give here. AB3, A and B are strongly coupled, but in the B there are 3 equivalent protons, that is why subscript 3. The same thing we can do for weakly coupled. I can call it AX2, A2X2, A2M2X2. AX2, there are 2 protons here which are chemically equivalent, that is a subscript 2, and A and X are weakly coupled. Similarly, A2X2, 2 protons are chemically equivalent, here 2 protons are equivalent, but A and X are weakly coupled, that is a nomenclature. Same thing for 3 protons coupled, 2 are equivalent here, 2 are equivalent here, 2 are equivalent here. A and M is weakly coupled, M and X is weakly coupled, A and X are weakly coupled. So, this is the nomenclature we use. Here is an example for that. Look at a molecule like this. Here there are 3 protons which are chemically equivalent, 2 protons which are equivalent, CH3 and CH2 group. It is a simple classic example of ethyl alcohol. What do you call this nomenclature for the spin system? A3X2. I am not worried about OH group. This is called A3X2 spin system. What about this molecule? We have a CH3 group here, CH2 group here, and a CH group here. Of course, this is 3 protons are there, subscript is 3, subscript is 2, subscript is 1. You call this as A3MX2 spin system. See A3MX2. What about this molecule? There is CH3 group, we have a CH2 here, we have a CH2 here. This is assuming they are far away separated, weakly coupled, I call it as A3 M2 X2 spin system. We will take example how we look at the spectrum of some molecule. Here is a molecule I consider 2 protons which is homonuclear weakly coupled spin system. Why I say weakly coupled? Measure this separation. I have given you chemical shift of one of the proton, let us say A, other is X. One is 3830 chemical shift in frequency, other is 3530. The difference is almost 300 hertz, and the coupling measured is 5 or 5.77. What is the ratio? 5 or 300 by 5 chemical shift delta delta difference over J coupling is almost 60. That means it is a weakly coupled spin system. Delta delta difference, and if you take measure the carriage, this is already calculated, and look at this intensity, they are of equal intensity, almost of equal intensity, and chemical shift separation is so large. So, very easy to analyze. This is a AX spin system. All I have to do is go to the center of this doublet, I get chemical shift of this, go to the center of this doublet, I get chemical shift of this proton. If this is A, this is X, I get delta A here, I get delta X here, I can get the chemical shift. I measure this separation, this gives you JAX. I measure this separation, exactly I get JAX, because interactions are mutual. Straightforward analysis, this is called first order analysis. So, first order analysis is possible in weakly coupled case. I can get J coupling and chemical shift by just looking at the spectrum by simple analysis, and look at it, all the lines are of equal intensity. Whereas, look at this molecule, here are 2 protons which are strongly coupled. Look at this peak here, central lines are of equal intensity, more intense than outer lines which are of weaker intensity. And also look at it, it is tilted like this. This is called a roof effect. And if I measure the chemical shift separation between these two, see, actually there is a small change in the chemical shift. And this chemical shift difference between 1 and 2 and 2, 3 and 4, if you consider, there are 4 different protons, 4 chemical shift frequencies have been written for all the 4 frequencies, all the 4 peaks here. What you can do is measure the separation between these two lines. This is about 688.7, okay, make it 688. Whereas this separation, if you measure this to this, average is 687. See, the difference is very small. Okay, here it is written JAB already, here chemical shift separation is about 2 hertz. We have worked out. Chemical shift difference between any of these 2 peaks, if we consider, I do not know which is A and which is B, I can't say. I can't say what is chemical shift of A and chemical shift of B here. Somehow let us say I measure the separation between these 2 lines and these 2 lines, and this is delta AB is delta nu AB or delta AB is 1.9 or 2 hertz, whereas coupling is quite large, about 3 hertz. If you take the ratio, this is much smaller. See, this is not 0.1 or 0.001 like that to be weakly coupled. This tells me this ratio, these 2 protons are strongly coupled. And in the case of roof effect, always what happen, some lines will be equal intensity, and then this tells me this is coupled in this direction. If this is weak intensity, this tells me it is coupled in this direction. See, this intensity is larger than this, so it is coupled here. This intensity is smaller than this is coupled this way. So, the direction of tilting, direction in which the intensity is changing, tells you which proton is coupled to which proton. This proton is coupled to this is coupled to this. This is called roof effect. And roof effect is a dominant phenomena you will see in strongly coupled spins. And in the weakly coupled spins, intensities are equal, roof effect will not be seen. Roof effect is seen in the strongly coupled examples. Take for example this molecule 2,3-dibromothiophene. At 100 megahertz, this is spectrum you are going to get. But you can see this and this are far away separated chemical shift, but you see the intensities are not equal. There is a roof effect in this direction. That means it is more close to AB than AX. It is chemical shift separation, if you see, you can say what is the chemical shift of this, chemical shift of this, more like an AX. But if you look at the intensity pattern, there is an AB character. This has a minute AB character in the AX spin system. So, it is could be AB because of the intensity. If you look at the chemical shift, it could be AX. So, it is the AX with the AB character, minute AB stinge is there in that. So, the spectrum, because intensities are not equal, you have to calculate it because it is a strongly coupled case. So, now we will take the examples of transitions you see in 2 coupled case. How do we get the transitions? How do we measure frequencies in the coupled case? This is the real analysis we have to start. Part of it we already discussed when I was explaining to you about the chemical shifts and J couplings between 2 spins. I explained to you about the transitions we get in 2 coupled spins. Just each spin sees the two other spin states of the other spin. There will be 4 possible spin states when 2 protons are coupled or 2 spins are coupled, which I explained to you. Alpha alpha, beta beta for down, both are down, both are up, alpha alpha, one up, one come down, alpha beta beta alpha. We already explained this. And the magnetic energy states of each of them are different. Magnetic energies are different. There are 4 different energy states. Small difference in the energies are there. And then we can get the total magnetic quantum number for each of the energy states. Total magnetic quantum number is the MZA, sum of MZA and MZX. That is what we have been discussing. I did not write explicitly, mathematically I did not work out, but I told you when the 2 energy states are there, both are plus alpha alpha states, plus half and plus half, the total quantum magnetic quantum number of that energy state is plus 1. One is plus half, other is minus half. The total magnetic quantum number of that energy state is 0 because it is the sum of MZA and MZX. for two spins you have MZA and MZ individually when you write for the particular state the sum is MZA plus MZX. So, as a consequence that is 0. Similarly, here plus of minus of plus of 0 minus of minus 1. So, Fz is the sum of the magnetic quantum numbers of each energy state. The spins can be both interacting and non-interacting, that is what I said. In there is interacting means coupling is non-zero, when there is no interaction coupling is 0. Still they can be coupled spin, but coupling can be 0, and if it is non-zero it is different. Of course, we call them as uncoupled spins when the coupling is 0. Transition into uncoupled spins if I consider, let us understand how do we get the transitions into coupled spin of nuclei. Of course, chemical shifts are different. Delta A is not equal to delta X and coupling I made it 0. This is my condition I have put to understand the transition that we see into uncoupled spin half nuclei. Of course, this we worked out. BA and BX are the two spins which are having orientation minus of with alpha A and alpha X plus of orientation plus of minus of plus of orientation. The magnetic quantum number is Fz is MZA plus MZX which you worked out minus 1 plus 1 0 0. Selection rule we apply that I have already discussed. During the selection rule when I explained, I took this example. This transition is allowed, minus 1 to 0 transition where alpha spin is flipping, alpha to beta, beta to alpha, that is allowed A transition. This is also allowed, alpha A to beta A is flipping from 0 to plus 1, that is A transition. This is alpha to 0 to plus 1 is allowed, 0 to minus 1 is also. This is alpha X spin is changing from alpha to beta, X transition. This is also allowed where alpha to beta of X is flipping, X transition. So, 2 peaks for A with identical frequency, 2 peaks for A, 2 peaks for X with identical frequencies are there, but identical frequencies overlap. Remember, there are 2 frequencies here, both are of identical frequency for A, identical frequency for X. Both the transitions have same frequency, that means there is a overlap. The frequencies are identical and they overlap. As a consequence, if there is no coupling, each of them A will give a single line, X will give a single line. That is what we understood. A will give a single line, X will give a single line. We assume chemical structure of one of them is larger than the other one, whichever is larger, whichever is smaller, that is our assumption. I assumed here chemical structure of X is more than that of A. So, X comes here, A comes here, and this is the chemical shift of X, this is the chemical shift of A. And remember, both are equal intensity, but appears a single line, but there are 2 lines overlapped. There are 2 transitions for A, 2 transitions for X, they are overlapped, gives us to single peak. This is for this is the spectrum of 2 protons or 2 spins which are not coupled, or in other words JAX is 0, 2 uncoupled spins. Let us consider the example of 2 spin half nuclei where coupling is there, that means JAX is non-zero and chemical shift is not same. They are not equivalent spins, chemical shifts are different, coupling is non-zero, and I assume chemical shift difference between A and X is sufficiently larger than JAX. Why did I assume? Because I consider weakly coupled. Remember the nomenclature which we discussed. So, 2 weakly coupled, the nomenclature is A and X. So, chemical shift separation between A and X is sufficiently larger than coupling constant. That is a weakly coupled case, and I have considered the example of 2 weakly coupled spin half Cs. In this case, we have to understand little bit more. What happens to the energy state when the spins interact? Remember, in one of the cases I also explained to you, the energy levels gets modified because MZA and MZX, when they have the same signs, alpha alpha and beta states are the two states where both have the same sign. Alpha alpha and beta beta are the states, they are called unpaired states. They are unpaired spins. Their alignment is less stable because they are unpaired. They have more energy. If you consider MZA and MZX, they have same signs, alpha alpha and beta beta, they have more energy states. If you consider alpha beta alpha alpha, I am sorry, these two energy states, if I consider alpha and alpha beta beta, they are destabilized. The energies will be pushed up by J by 4 because they are unstable, they are less stable, not unstable, I would say less stable because of unpaired, they are destabilized and the energy will be pushed up by J by 4. What about other spin states? Consider alpha beta and beta alpha, they are plus half and minus half, they are paired. When they are paired, their alignment is more stable. Like spins are always, they are destabilized, less stable, more energy. These have less energy because they are stable, they are paired. So, alpha beta and beta alpha are paired states. Then what will happen? Their energy will be pushed down. What is the energy? How much energy it is pushed down? Compared to alpha alpha and beta beta, they are pushed up by J by 4. They are here they are paired state, they are pushed down by J by 4. You understand the difference? If you consider the energy states, alpha alpha and beta beta are pushed up because they are unpaired states, unpaired spins, whereas alpha beta and beta alpha energy states are pushed down by, they are decreased by J by 4. So, this is what happens. In the earlier case, both the energy states, there was say identical, there was no pushing up, there was no stabilization and destabilization because coupling was 0. Now, in the coupling I have assumed there exists a coupling between J and X, A and X spins. Now, this state beta beta is pushed up by J by 4, alpha alpha is pushed up by J by 4, whereas beta alpha and alpha beta are pushed down by J by 4. See, energy states are now not same, they are different, but remember what is the energy identically. If you can calculate the transition between different states, or I consider 1, 2, 3, 4 energy states, we will find out what is the transition. 1, 3 is allowed where A is flipping and 2, 4 is allowed, again A is flipping, but look at this frequency separation compared to this frequency separation. This separation frequency is larger because delta E separation is larger compared to this. That means they are not of the identical frequencies. In the previous example, when they were uncoupled, frequencies were same, but here the frequencies are different. One has a larger frequency, other has a smaller frequency. The larger frequency you see is different and smaller frequency is different because one is pushed up by J by 4, other is pushed down by J by 4. Similarly, for X spin, this is the frequency allowed and 1, 2 and 3, 4 frequencies allowed. This is allowed. See, 1, 2 frequency is larger because of energy larger, separation is larger, and 3, 4 frequency is smaller compared to 1, 2. So, X frequency also has 2 frequencies, X spin has 2 frequencies. One is larger frequency, other is smaller frequency. A has 2 frequencies, one is larger, the other is smaller, and how much it is that you can work out, you can calculate mathematically, which I am not going to do that because this has been already discussed in one of my previous course. Without going into rigorous mathematics, I tell you 4 energy states, alpha alpha, alpha beta and beta alpha are like this. For this thing, the energy states you can calculate eigenvalues of half of nu A plus half of nu X plus 1 for J X. For this one, half nu A minus half nu X minus 1 by 4. For this one, minus half nu A plus half nu X minus half, whereas this one both are minus half minus nu A and nu plus of 1 for J X. Very easily you can calculate, quantum mechanically you can work out the eigenvalues, and then the difference in the eigenvalues gives you the frequencies. For example, 1 and 2 if you calculate here, go back here 1 and 2, you take this 1 and 2 and calculate the difference, and you will get nu x minus half j a x. Difference between 1 and I am sorry, not 1 and 2, this should be different. If you take the this number is by mistake, cut and pasting while I have made a mistake, it is not this 1 and 2, this is different, and if you calculate that difference, then you will turn out to be nu x minus half j a x. So, that means for the x spin there are two transitions, one is plus half j a x, other is minus half j a x. There are two frequencies for x spin. Similarly, you can calculate for 1 3 and 2 4, one is plus half j a x with respect to A, other is minus half j x with respect to A. One gives chemical shift of A plus half of j x, other is chemical shift of A minus half of j x. So, essentially what happened? If you calculate mathematically, quantum mechanically, you have to write down the Hamiltonian, diagonalize the Hamiltonian, calculate the eigenvalues, get the frequencies and get the difference of the frequencies by applying your selection rules. You can see that proton A will give 2 peaks, one is shifted up by delta A by plus j by 2, other is shifted by delta A minus j by 2. Similarly, proton X will give 2 peaks, one is shifted from chemical shift of X by j by 2, other is shifted from chemical shift of X by minus j by 2. That means proton A will give 2 peaks from the center moved by same value, from the center moved to the other side by same value. Same way with delta X, there are 2 peaks from the center, one moves by j by 2, other is moves by minus j by 2. Exactly, you get 4 peaks for 2 coupled spin system gives maximum of 4 peaks. Okay. 2 for A and 2 for X. So, center gives me chemical shift of A, center of this doublet gives me chemical shift of X, and the separation as I calculated, I showed you they are moved just exactly by plus j by 2 and minus j by 2. If you take the difference, you will get j a x. Similarly, you take the difference, you get j a x. So, when two protons are coupled, chemical shift of one of the doublet gives you chemical shift of A, chemical shift of the other doublet gives you chemical shift of X. The separation always gives you j a x, whether you take this separation or this separation, the separation gives you j a x. So, that is what I said, 2 coupled spin gives maximum 4 peaks. For n coupled spins like that, we can calculate, I will come to that later, but today since the time is up, I am going to stop it. What I am going to tell you is, in this class what we had discussed is, we understood more about the nomenclature of this Popper nomenclature for the equivalent spins and chemically equivalent spins, and when there are more number of spins, for example CH2 groups, CH3 group like that, when there are more spins chemically equivalent for a given, then we use this a subscript notation. When they are chemically equivalent, I said we use prime notation. Again prime notation can be used for weakly coupled and strongly coupled. For example, weakly coupled we can use A prime XX prime. For strongly coupled we can use A prime BB prime. For equivalent spins we can say A prime A2 prime B2 prime, whereas or A prime BB prime, whereas in the strongly coupled case we can say A2 X2 A2 prime X2 prime, like that A prime XX prime. Varieties of nomenclatures we can use, and I took the example of 2 spins, J coupling 0, J coupling non-zero, and I wrote down the energy states for alpha alpha beta beta alpha beta beta alpha. It is nothing but the total magnetic quantum number is nothing but Fz, which is called mz of A, mz of X. For beta beta is -1, alpha alpha is +1, alpha beta is 0 plus beta alpha is 0, and for j a x is 0, we get 2 transitions for A, 2 transitions for X, identical frequency for A which are overlapped. Similarly, 2 frequencies for X are identical overlapped, we get 2 only singlets. Whereas, if the J coupling is there, alpha alpha and beta beta are unpaired, as a consequence they are destabilized and these energies are pushed up by J by 4 when there is an interaction. Whereas, alpha beta and beta alpha are paired ones, their energies are more stabilized, pushed down by J by 4. Now, if we calculate the frequencies, in this case coupled case, we found out A will have two frequencies, one pushed up by j by 4, j by 2, other is minus j by 2. That means from the center you have one peak which is moved by j by 2, one peak which is moved by j by 2, from the left, one to the right. The separation gives you j. Similarly, for x spin, from the center of the chemical shift of x, one peak is moved by j by 2, other is moved by j by 2, and the difference gives you j, Ax. From the center of this doublet gives you chemical shift. Like this, for two coupled case we showed there are only 4 possible transitions, okay, A and X, 2 for A and 2 for X. So, more we discuss for when we have more coupled spins, how many peaks we get, etc. in the next class. So, I am going to stop here. We will discuss more things in the next class. Thank you very much.